Okay, so what we're going to do is we're going to actually solve a system of equations using the LU factorization approach. And I'm going to be showing you how to find an LU factorization to help you solve the system of equations. So let me give you just a moment to copy this down. All right. Okay, so this is naturally, we want to think of this system then as a matrix equation. A times X equals B. And of course, B is a 4 by 1. What's the dimension on your solution vector X? What are the dimensions on that vector? Four by 1. That's right, Hung. There are four variables. Four variables. And so the matrix A has to be a, what are the dimensions on the matrix A? Good. Good, Abby. 4 by 4. And of course, the matrix A is the coefficient matrix that contains all the coefficients for this problem. So let me go to the next page. All right. So let me see. Just one moment here. I actually have it a little bit out of order here. Okay, this is the page I want. So, of course, A times X equals B. And what we want to do, now wait, I'm sorry. No, I had it in the right order. Let me go back. Now, all right, so what I want to do is I want to find out what the LU factorization is for this matrix A. Okay, and really to understand this, you almost, I mean, I could like just, hey, in the book, here's how you do it, but it's much better if you copy the process down. So I'm going to have you copy, the left side here and the right side. And I'm gonna talk, well, I mean, go ahead and start copying up here, the left side and the right side. And what I'm doing on the left side is I'm taking the matrix A and I'm doing row steps to get that matrix A in echelon form. In this case, of course, we can say that's upper triangular form. And then I'm doing something on the right. I'm doing something on the right, and I'm going to talk about that. So, but what I'd like you to do is just copy down up to here. Copy down up to here. And then I'll talk about what's going on the right side. Okay? So let me give you a moment to do that. Okay, all right. So we're gonna do this algorithm that's going to allow us to find what's called the LU factorization of the matrix A. So we're going to be writing the matrix A as a product of a lower unit triangular matrix times an upper triangular matrix. And here's how the algorithm works. Okay, so of course on the let me see here. Let me. So what I do is I have the matrix A and I focus on this first column. And what I do is I take that first column and I put it in another matrix. So essentially what I'm doing is I'm going to be constructing the, like while I'm getting the matrix A in echelon form, while I'm row reducing it to an upper triangular matrix, at the same time, I'm going to be constructing my lower unit triangular matrix L. So I'm building the matrix U and the matrix L simultaneously. All right, all right. I bring over the first column over here. So on the left side of this this dark line in the middle, like in the middle, on the left side, I'm row reducing the matrix A to get it in echelon form. And on the right side, here on the right side, I'm constructing my matrix L. Of course, it won't be done till the very end at the bottom. All right, so what I did here was I did some row operations. To get zeros in the first column below the 3. And naturally, I'm using the 3 here as a pivot. I'm using the 3 as a pivot. So I did divide through by 3 on the first row because that would introduce fractions, and I want to make my life easy. Can't always avoid fractions, but I can so far. All right, so I get to this step, and then what I do is I look at the second column, and I take the bottom three numbers in the second column, the -2, the 10, and the 16, and I place them in the second column, okay, in this matrix to the right that I'm building. Okay, and you'll see why this is going to work. All right, well then what I want to do is I want to naturally use the -2 here as a pivot and to get zeros where the 10 and the -16 are. And so I do these row operations, and when I do those row operations, you know, I get this row equivalent form of the matrix A. And now what I do is I look in the third column. In the third column, I look at the last two numbers, and I put those last two numbers over here in my matrix to the right. Okay. And then finally, I get down here, and my matrix is now in upper, well, hold on here. No, I'm not there yet. Now what I want to do is I want to use this -1 as a pivot to produce a 0 where the -3 is. And so I take -3 times the third row, add it to the fourth row, and place the result in the fourth row. And then this is my resulting matrix. And the fourth column, the very last number, the fourth number, the -1, I place it here. Okay. So now I have a matrix. Now the matrix A, I get it in row equivalent form. So it's now in matrix U. Matrix U, that's what this matrix is here. And it's in echelon form, but that's upper triangular form. On the right side, what I do in the algorithm, what I do is I want to have ones along my diagonal. Okay, I want to have ones along that diagonal. And so now this is an algorithm. So what I'm saying is in this algorithm, like what I'm going to do is I'm going to take the first column here, and to get a 3, to get a 1 where this 3 is, I'm going to divide the first column by 3. Now, technically, right, you can't divide columns by numbers. You can divide rows by numbers, but you don't divide columns by numbers. But in the algorithm, you just do this. You just do this, and it's all going to work out. So just do it. Don't worry about that. It's not like, you know, mathematically correct. Just do it and don't worry about it. In the second column, -2 is there on the diagonal. Well, I want a 1 there, so I'm going to divide the entire second column by a -2. Third column on the diagonal, I have a -1. I want a +1 there, so I'm going to divide the entire third column by -1 in the algorithm. And then finally, the fourth column here, we have a -1. I want a +1 there, so I'm going to divide by -1. Okay, so the result is then I get a matrix L, and by the way, I didn't put zeros here, but where these spaces are, but it's understood that there are zeros there. It's understood that we have zeros here. Okay, so what happens, that's a 0. What happens then is, hold on, I can make that a little nicer. All right, that's a 0. Okay, so what happens is then I get finally, I get this, well, hold on now, I don't want to do that. Hold on. That's a 1 there. I'll just have to, you know, here we go. So finally, I get this matrix here. And that matrix is in lower triangular form because the, you know, on the left here, the matrix U is in upper triangular form because you have a triangle of zeros below the diagonal. But here on the right side, this matrix L, I have a triangle of zeros above the diagonal. So this matrix is lower triangular. But because the diagonal of that matrix it's a diagonal of 1s, we call the matrix L lower unit triangular. And I can promise you, you can check it out in MATLAB if you want. Why don't you check it out in MATLAB and see, does A equal L times U? Why don't you take a moment in MATLAB? Let me give you a few moments to type in the matrix U and the matrix L and verify that A equals L times U. I mean, on your next exam, this kind of problem, you would want to check that, right? Before you committed to your answers. So do a check and let's see if we have some believers here that the matrix A equals L times U. And incidentally, the matrix A is 4 by 4, the matrix L is 4 by 4, and the matrix U is 4 by 4. So L times U is defined very well. And, you know, the product would be a 4 by 4 matrix. The question is, are you convinced it equals the matrix A? So I'm going to wait for a few moments here, and let's see if we have a few people who will confirm that in MATLAB. So you're checking to see if L times U equals A. I'm just going to stand by here. Okay, so I'm going to wait a few more minutes here to see if I get a confirmation. I guess I'm hoping most of you are trying to confirm this. Justin says it didn't quite work for him. Okay, thank you for your honesty, Justin. Okay, hang on. Well, in a way, I guess I'm glad that, okay, all right, Samantha, I'm happy. Benjamin, I'm happy. All right, we have 2 confirmations. Let's see if and thank you everybody for your honesty. Let's see if the other folks, the other 3 checking can maybe, so I'm happy about that. Okay, good. All right, Ariana, great, and Catherine. Okay, so Catherine, you just, all right. Well, so this is true then. A equals L times U. A equals L times U. Okay, good. Justin got it. All right, thank you, Catherine. Catherine got it. Wonderful. So now, you know, we can proceed on with the problem, but there's an interesting thing here to notice. A couple of key points here. First of all, no row interchanges were used here. Okay, so like, of course, for your when we did the row operations that got that row reduced the matrix A to the matrix U, we didn't do any row interchanges. If you see, normally like MATLAB, when it does an LU factorization, it will do row interchanges because it's doing what's called permuted LU factorization. Okay, but and we're going to talk about that. We're going to talk about that because one of your MATLAB assignments is going to be based on that. But for the section 2.5, like homework problems in MyMathLab, you're not going to be using MATLAB to help you get the LU factorization, and I don't want you to. I want you to work out the LU factorization by hand. But you do not do any row interchanges. No row interchanges. Okay. And also, you know, for section 2.5. Also, another thing too that's key here. The same row operations Okay, this should be, hold on here. One moment, class. I guess it's got, hold on, class. One moment. One moment. Okay, so this word here, this word here is operations. So I'm going to try to, let me try to use my my little device here to write that in. One moment. Let's see. Let's see here. So we'll see how this goes. One moment. I'm getting a, for some reason, boy, chords are a pain, aren't they? Chords. Chords are a pain. All right. So all right, I want to write the word. Okay, perfect. So the same, now I'm going to go back to this. The same row operations that reduce the matrix A, okay. I don't know why some of this, it's just a, I work very hard on this. I want everything to show properly. All right, so I'm focused here. Focused right here. All right, the same row operations that reduce the matrix A to U will reduce the matrix A to the identity. Okay, very, very important. Okay, I'll repeat that. Again, I'm emphasizing this point here. The same row operations, and make sure, please, you have it correct in your notes. The same row operations that reduce the matrix A to the upper triangular matrix U will reduce the matrix A to the identity matrix. The same row operations that reduce the matrix A to the upper triangular matrix will reduce the matrix A to the identity matrix. Now let's see, if that's true. Let's see if that's true. Okay, so what I'm going to do is I'm going to look, for instance, hold on. Okay, I'm going to focus on these three row operations. Okay, hold on, this isn't right. This is not right. I said this wrong. I said this wrong. This should be an L, and this should be an A. Okay, so let me correct myself here. The same, so I'm talking this box here. This is very important. That's why I don't want to. The same row operations that reduce the matrix A to the upper triangular matrix U will reduce the matrix L, okay, the lower unit triangular matrix. It will reduce it to the identity matrix. So again, the same row operations, please make sure you have this correct in your notes. The same row operations that reduce the matrix A to the upper triangular matrix U will reduce the matrix L, okay, this matrix, to the identity matrix. The same row operations that reduce the matrix A to the matrix U will reduce the matrix L to the identity matrix. So let's see if that makes sense. Let me focus here on these three row operations. Okay, let me focus on these three row operations. So let's say I were to add the first row here. Let me just okay, so the first row operation is add rows 1 and 2 and replace the result in row 2. Well, if I add this row and this row, okay, the first and second rows, what are we going to get in this spot right here? What are we going to get in that spot right there? If I add the first, if what I'm trying to say, let me be more clear here. Take this row operation, okay? Do this row operation on the first and second row, and you're going to get a 0. Very good. You're going to get a 0 right where that -1 is. If you add the first row to the second row and replace the second row with that result, you're going to get a -1. You're going to get a 0 where that -1 is. Let's look at the next operation. Next operation says take -2 times the first row and add it to the third row, and then replace the result in the third row. Okay, if you do that, okay, if you do that on this matrix L, what would you get? What would you get right? What would you get in that spot there? What would you get? You'd get a 0. That's right, Nafani. That's right. Let's say now you take 3 times the first row, add it to the fourth row, and we replace the fourth row by that result. What would happen to the -3? What would it become? It would become a 0. Okay, so, and that's what would happen. That's what would happen. Okay. All right, now let's focus on the next set of row operations. Okay, let's focus on the next set of row operations. Next set of row operations, okay, says take 5 times the second row, add it to the third row, and replace the third row by that result. So if you take the second row and add it to the third row, if you took 5 times the second row and added it to the third row, what would you get here? So, you're using the 1 as a pivot. You get a 0. Good, Haley. And then if you were to take -8 times the second row and add it to the fourth row and replace the fourth row by that result, what would you get here using the 1 as a pivot? So if you took -8 times the second row and added it to the fourth row, you'd get a, that's right, Catherine, that's right, Ariana, you'd get a 0 here. Okay, let's look at the final set of row operations right here. The final set. Final set says take -3 times the third row and add it to the fourth row. Replace the fourth row by that result. So using this 1 as a pivot, okay, if you added the third row to the fourth row, what would you get? If you took -3 times the third row and added it to the fourth row, what would you get there? Where the 3 is, what would you get? You get a 0. So basically, if you were to do all of these row operations here on this matrix L, those row operations would reduce the matrix L to the identity matrix. And that's why I'm saying the same row operations that reduce the matrix A to the matrix U will reduce the matrix L to the identity matrix. And so that's why this algorithm works. Okay, are there any questions on that? Who's feeling a little bit comfortable? Who's feeling reasonably comfortable? Okay, Natalie's seeing it, Haley's seeing it. Is there anybody who's a little bit uncomfortable? You have to ask me if you're uncomfortable. If you need to convince yourself, I mean, just remember, if you do all these row operations here on this matrix L, you will get the matrix L reduced to the identity matrix. Okay. And that's the key behind this method working. But let's continue on here. Okay, so now we have that A times X equals B, and A equals L times U. So I'm going to then, since matrix multiplication is associative, on the left side, I'm going to write then L times U X equals B. And U times X, I'm going to call that Y, the vector Y. I can do that because, remember, in this case, the matrix U, that upper triangular matrix, is a 4 by 4. Hold on here. It's a 4 by 4. The vector x, we know, is a 4 by 1. So that means the vector y is a 4 by 1. So I'm solving this intermediate system of equations for the vector y. But once I know the vector y, I can then solve a second system of equations for the vector x, which is the solution I want to get. Now you might wonder, Dr. Judy, it takes enough time to solve one system of equations. Why do we want to solve two systems of equations? Well, let me show you, like in this case, why this method's going to work great. So here's the augmented system, the augmented matrix for L times the vector y equals the vector b. And I'm going to use this 1 as a pivot to produce, then with row operations, I'll use the 1 as a pivot to produce zeros in these 3 spots. So I'll do these 3 row operations. Okay. And I'll get this resulting matrix here. But let me ask you, is it difficult to get this matrix based on the first matrix here? Is it difficult to get this matrix? Were there a lot of math operations that needed to be done? So what I want you to do, I want you to focus on like just for now, focus up to here. We did 3 row operations. So whenever you do row operations, there are mathematical operations, or what we call flops, involved. Okay. Is getting this matrix here difficult? Or is it easy? Were the row operations easy? Benjamin says it was not difficult. Okay, why? Why wasn't it difficult? The row operations. I mean, look. Did lots of zeros. Good, Hung. Lots of zeros. I mean, look here. Look at these numbers. These numbers here didn't change. They didn't change. Right? And that's because you have lots of zeros. So this cuts down on the mathematical operations or flops that need to be done. And if you're using a computer, it cuts down on the operations. It'll cut way down on computing time. Okay. Are there any questions on that? Okay, well now what we do is we're going to use this 1 here, okay, as a pivot to produce zeros where the -5 and the 8 are. But again, because we have, lots of zeros here in our second row, when you do the row operations, okay, when you do the row operations, a lot of the numbers just stay the same. Okay, so this is the beauty of this. And in the end, of course, you're going to get, you're going to get y1 equals -9, y2 equals -4, y3 equals 5, and y4 equals 1. And so now you know the vector y. The vector y is the vector that equals, it has entries -9, -4, 5, and 1. Are there any questions? Are there any questions up to this stage here? Are we ready to move to the next page? All right, very good. Very good. Well, then let's move to the next page. All right, now I want to solve the system of equations u times x equals y. So here's the augmented matrix. But now, because we have a lot of zeros here, again, it's going to make our lives easy for the row operations. And you go through the steps, and without too much difficulty, you're gonna end up with this final augmented matrix, and you'll be able to determine that x1 equals 3, x2 equals 4, x3 equals -6, and x4 equals -1. Let me give you a moment to copy it down. Please let me know if you have any questions. So you always have to think, these methods, of course, when you're dealing with smaller systems of equations, pretty much you can do any of the methods that you've learned. And now but it's when you deal with bigger systems of equations where some methods are going to take more computing time than others. And even with the smaller matrices, some methods are more efficient than others. But all right. Let me go to the last page. Are there any? Does everybody have this copied down? Does anybody need a little more time to copy? Okay. All right. No problem. No problem. Okay. Maybe give a thumbs up when you're ready to move to the next page, and we'll. I mean, we're almost done. All I want to do is state the solution vector x. That's all I want to do. Okay, very good, very good. Thank you, Nafani and Shravani. Okay, so here's your solution vector x, and we're done. Okay, I'm going to bring up the lay textbook for a moment. Let me see here. Okay, so let me just show you a quick proof of why this method works for uh, being able to write a matrix, say, as L, a lower unit triangular matrix times times a upper triangular matrix. All right, so let me just bring up the book here. If I'm able. Yeah. Let me see, is it sharing it? Hold on, wait. I thought I had that thing open. All right, hold on. You have to give me a moment, class. Okay, so okay, one moment. Okay, good. All right, so let me bring up the book. See, I don't give up when I encounter problems. You know, you can't give up. Can't give up. You can get a little frustrated, but don't give up. All right, so hopefully you're seeing the book. Good, good. So the LU factorization algorithm, okay, the proof of that is actually not, it's not that hard. Well, I mean, it really is quite simple. Okay, so remember you elementary matrices, when we showed why the algorithm for converting the algorithm for finding the inverse of a matrix, I showed you that algorithm worked based on an example where I had the product of elementary matrices. Elementary matrices multiply the matrix A, and elementary matrices corresponded to row operations. So when you do row operations and you work them out in your mind, mathematically, the row operations can be represented by taking a sequence of elementary matrices and multiplying them by the matrix A. And we know for every row operation we did in the example we just learned about, to convert the matrix A to get it in, to get it as a LU factorization. Every row operation we did can be represented by an elementary matrix. And so a sequence of elementary matrices multiplied together by the matrix A would produce, would be equal to the echelon form which is the upper triangular matrix form. I want to say this right. The reducing the matrix A to the upper triangular form took a sequence of row operations. Each one of these row operations can be represented by a corresponding elementary matrix, which is just, you take the identity matrix and do an equivalent row operation on the identity matrix to get the corresponding elementary matrix. So E sub P minus 1 times ... E sub 1 A equals U. And that means then that A, hold on here, that means that the matrix A can be thought of as the inverse of the product of those elementary matrices times U. And that would therefore have to equal L times U. So L is equal to the inverse of the product of those elementary matrices. Okay. Now, if we go to the next page, remember I had said that the row operations that we use to reduce the matrix A to the matrix U, those equivalent row operations would reduce the matrix L, the lower unit triangular matrix. It would reduce that matrix L to the identity. And that's true because the matrix L is just equivalent to the inverse of the product of those elementary matrices. And so this then, the product of the elementary matrices times the inverse of the product equals the identity. And that's the key to constructing that matrix L. That's why this works. Okay, how many think this is pretty cool? A pretty cool algorithm. Okay, Olivia likes it. Thank you, Olivia. All right, maybe we can get one other person. I don't know. All right, Ariana likes it. Is anybody a little bit nervous about it? Thank you, Ariana. There might be a few of you that are a little bit nervous, but don't worry. Okay, Eleanor likes it. Wonderful, wonderful. All right, thank you, Eleanor and Olivia. And so more on this algorithm. If we keep like going to the end here, it talks about how an LU factorization of a matrix A takes about 2n cubed over 3 flops. Okay, whereas finding an inverse takes about 2n cubed flops. So for instance, if you're going to solve a system of equations, okay, if you were to go x equals A inverse times B, well, finding that A inverse takes 2 times n cubed flops. So for instance, if your matrix is a 4 by 4 matrix, then that would take, finding the inverse would take, let's see, 2 times 4 cubed. That's 100 and, hold on here. I should know that. It should be 128 flops, right? 2 times 4 cubed. That's 128 flops. But if you do the LU factorization, it's going to take about 42 flops. Of course, you still have to solve the system of equations then, but that takes a lower order, 2n squared flops. Okay, so it would take then 42 flop to solve a system of equations using the LU factorization approach for a 4 by 4 matrix. Okay, and we're assuming here the matrix is dense. That means the matrix doesn't have like 0 entries in it. So using the inverse approach, you know, x equals A inverse times, I want to be careful here. Hold on here. In step 3, they talk about multiplication of B by A inverse takes about 2n squared flops. Okay, so essentially, to use the inverse approach, to get the inverse takes 2 times n cubed flops, and then to multiply A inverse by B, that's step 3, you know, so step 1 says finding the inverse takes 2 times n cubed flops. I don't want to say step 1, comment 1. Comment 1, let me just, hold on. I want to be as clear as possible. Let's focus on, hey, you know, what if we solve a system of equations by doing x equals A inverse times B? To find the inverse, it's going to take 2n cubed flops, and then, that's in comment 1. Then comment 3 says multiplication of B by A inverse requires 2n squared flops. So that means the whole process takes hold on here, the whole process would take 2n cubed plus 2n squared flops. So if n equals 4, that would be, if you have a 4 by 4 matrix A, that would be 2 times 4 cubed plus 2 times 4 squared, which is 128. Hold on, there was a chat thing here. Yeah, that's 128 plus 32, which is about 160 flops. So that's 160 math operations. Okay, whereas, okay, if you were to do it, if you were to solve a system using an LU factorization, getting the LU factorization takes about 2 times n cubed divided by 3 flops, and then solving the two systems of equations takes about 2n squared flops. So for a 4 by 4 matrix A, the number of flops would be approximately 2 times 4 cubed over 3 plus 2 times 4 squared. Well, 2 times 4 cubed over 3 is about 42, and then you're going to add 2 times 4 squared, which is 32. So 42 plus 32 is about 74. So roughly 74, 75 flops. So which is better, 160 flops to solve a system using an inverse, or 75 flops to solve a system using an LU factorization? And you know, and I'm talking in this case for a 4 by 4 a matrix with 4 equations, 4 unknowns. Which is more efficient, LU factorization approach or the inverse approach? There you go. A flop, that's right, a flop, Olivia, is a mathematical operation. Adding, subtracting, dividing, or, adding, subtracting, dividing, or multiplying. That's what a flop is. Okay? It is interesting. It's very interesting. And, I could just kind of ignore this, but hey, now I'm trying to open up your world more, I'm trying to help show you the beauty in linear algebra. And well, Olivia, and you learned something really cool here. You learned something really cool. One thing I'll mention too here is that LU factorization, okay, can be done on any size matrix. So if you look at example 2, they do an LU factorization for a matrix with 4 rows and 5 columns. Okay, so they do an LU factorization on that. So feel free to look at that example. In your homework, you're going to have some problems where you have non-square matrices where you have to do an LU factorization. All right, so are there any questions on this material, section 2.5? Okay, well, on that note, I'll stop the recording.